To begin this video today with a conversation about Plato, and specifically about his concept of Platonic forms. If you're not familiar with Platonic forms are essentially the perfect idealization or the perfect form of something. I can utilize really simple objects to illustrate this concept. We'll utilize the concept of cup or of chair. And within Platonic forms, there exists a Platonic form of cup or a Platonic form of chair. And these would be the idealized, perfect form of these concepts. The perfect chair would be the Platonic form of a chair. If we take that a step further, we can kind of examine the elements of what would make the Platonic form of a chair. It would be the most comfortable chair that could possibly exist. It would have four legs. It would be the ideal geometric shape for sitting, whatever that would be. And so we can essentially envision aspects of this, and then by envisioning the dimensions of the Platonic form of chair, we can come up with Platonic form of chair. And what's important to extrapolate from that as kind of the next concept is that if this Platonic realm exists and that there's Platonic forms of everything, then essentially the real world, the world that we operate in, is essentially an abstraction of the Platonic forms, meaning that my shoes are not the Platonic form of shoe. They're an abstraction of the Platonic form of shoe, right? They're not the perfect shoe; they are a shoe, and then they're an abstraction of the concept of shoeness. And I frame this. It's a very important framing to before diving into this particular research paper, and I'll show you and I'll frame it out to you why in a second. So this particular research paper that we're going to dive in today is called Cross Entropy is All You Need to Invert the Data Generating Process. And this is a very interesting and straightforward research paper. So essentially, for a while now, the big question has been that AI models and LLM models and and a lot of neural networks, they produce an output that is not linear, meaning that if you have an input, it generates an output, and that we can't decipher how that output is made. And then because there's an aspect of probability within that. And mathematicians have essentially theorized from the beginning that there's a relationship between probability and linearity, that they're tied together, but no one has been able to prove it, right? And so the kind of like the hypothesis is and has been that you can take these probabilistic outputs and that there is actually some sort of linear process that occurs. There's something linear that you could apply to it, and you could essentially like unravel the logic of it. You just need to know what the linear lever is, and that's what we haven't been able to figure out. Like, what is the linear lever that exists within these probabilistic equations? And a lot of people have been focusing more and more on topology and shapes and geometry. And that's what this paper boils down to, essentially. And then so essentially what this paper does is it utilizes and it goes through the concepts of self-supervised learning as well as supervised learning. And then essentially tries to model and understand how the models actually learn this process, right? Like, what is the what data do they take in when they're going through this supervised and self-supervised process? And very specifically, they highlight and they talk very specifically about the self-supervised process, learning process, right? Because like, if there weren't actually learning occurring, then self-supervised learning wouldn't actually work. So what is it that makes it work is kind of like the essence of what they try to explain. And then what their theory is and what they break down within that is pretty straightforward, in that essentially what happens is that the model takes in these data sets as shapes. And then so let's take a book, right? Like Harry Potter. And then so it will initialize the shape of Harry Potter. And then it will do that based off of dimensions of the book. Within Harry Potter, the concept of Harry Potter involves a lot of like magic. It involves magic, muggles. These would be like Hogwarts. These would be like very common concepts within Harry Potter, right? So these would all make up dimensions of Harry Potter. And then when you shape those into different shapes, each one of these different concepts that I mentioned would be a node of the shape. So you would have like Muggle would be a node, Hogwarts would be a node, magic would be a node, etc. Right? And then you would just go through, and then by putting all of these nodes together, you come up with the essence or the Platonic form of Harry Potter. And the essence or the Platonic form of Harry Potter would be different than the book, which is important. This is the important kind of distinction within this, right? And where it starts blending philosophy within this. But what this paper is proving, and that's why it's been hard to prove, but when you dissect and you look into this paper, their math and their concepts, especially in the appendix here, they go through the whole entire mathematical concept of it. Where essentially they're able to map this out. Okay? And then so they utilize it via cluster vectors. And then so cluster vectors are like this, like little dots that we're thinking of here, right? And it's imagine it exactly as I just laid it out. So if you take the book Harry Potter, like all of these different clusters of Harry Potter, like when the model initially maps out Harry Potter, it maps it out into different clusters of terms, right? So this might be magic, like purple might be magic. This like bluish tinted one might be Hogwarts, and then this yellow one might be Muggles, and then that's what it goes through, and by combining all of these different cluster shapes and the shape of the clusters themselves, you get that topological shape that emerges, a representation that emerges within that. And that's the important concept within this, right? Like essentially how I break this down in my mind as to what the models are doing in this instance is that they're creating the Platonic form of representation of the concept, which is it's kind of a very unique concept, right? And it's the Platonic form of representation itself is what we're looking at. And then to me, like the Platonic form of representation itself can be boiled down to clustering mechanics and the topology of those clustering mechanics. And based off of that, you can essentially from there you can get to binary, to languages, etc., and expand from there, right? But the first is understanding clustering mechanics. The second is understanding shapes and topology associated with those clustering mechanics, and then you build from there. So like what's the essence of learning? It's this, essentially, to me, is kind of what we're boiling down and looking at within, right? And then so I wanted to, so very first thing I did is I took the research paper and then I read through it, understood it, and then I wanted to visualize it for myself, right? And then so that's what we're looking at here in this first cell. And I wanted to understand, okay, so like I understand the models, they take these shapes and they essentially they create shapes out of data, and then so again, like these shapes could be our Harry Potter example. These shapes could be anything, a concept, right? But the concepts themselves are our shapes, and then so it starts off with an initialization of the shapes. And then as you train it on Harry Potter, for example, then it goes through and then the shape will change. And then so we see the original data versus the data after training. And then that's what happens. It changes the shape and the topology because it learns more about the data, right? It's the original data is based off of just like, let's say like an initial scan, like you give it Harry Potter and it's just like 5-second scan of the book will tell you a lot about the book, right? And then, but when you train on that book, you're going to find a lot more information than just that 5-second scan, and it's going to change the shape of that representation completely. And then, so that's what you end up with as kind of the end result there. And then so like, and then I want this to fully map this out, right? So okay, I understand how this works, but then like the question that I have within that, and I need to break down for myself after I do this, is like, how does it come up with this initial shape? Like, what are these initial dimensions? And so in this example, I utilize the book Moby Dick, and then essentially just understand and try to understand like how exactly does the model initialize this? Like, what are what's the initial shape of this book, right? And then essentially what I do, so I go through this analysis and I come through it, and then the initial shape is essentially what the themes are of the book. So obsession, awe, creature, powerful, and madness are like, this is the pure essence of the shape of the book Moby Dick, which makes sense, right? Like the number one word would be obsession, and like that is defining of that book to me very clearly, right? And just that one word, the very first word, obsession, awe, creature, that tells you everything that you need to know really about the book in 3 words, and then visualizing that into actual latent space. Like like imagine again, these dots are obsession, awe, creature, powerful, madness, little, unknowable, infinite, art, tail, man, and then these are the shape, right? And then so this shape essentially is what the shape of the book ends up being as a result. And when you do that analysis and you break that down, and then so this is the Platonic representation, the Platonic form of the representation of the book, right? Which is different than the book itself. The book is an abstraction of the Platonic form of, in this instance, Moby Dickness. The book itself is an abstraction, and then so we can take that abstraction and we can essentially build a higher level layer abstraction than that abstraction. We can build a better abstraction, and essentially build and understand the core essence and the core elements of that. And then so if I were to break this down kind of like into simplistic terms, like to me very clearly what this means is that I could essentially take and utilize this data, and then I could reconstruct. Let's say that you task me with reconstructing either like a movie or a book of Moby Dick, and I could any genre, any timeline, any time frame, any time period, etc. I can take the essence of this book and just understanding these mechanical components of it, and I will get you the essence of that story throughout different time periods or throughout different settings, etc. Because I'm going to make sure that the core essence of it remains throughout, right? And then the core essence of that particular representation, because I understand the shape of that representation. And then so that's what this whole research paper to me comes back to is this, right? And that's what they clearly outline, is that the solving that gap, the linearity gap between the probabilistic inputs and what actually occurs. And then what's actually occurring is it's creating shapes off of these, which we know. And then it's essentially step one is that it's recognizing that there's a noisy representation, that we have a book or a piece of text, and that this piece of text is a noisy representation of a larger concept. So the book Harry Potter is a noisy representation of Harry Potterness, for example. So we know that, and we have our element, and then so we deconstruct the element of it. Like, what is the essence of this? What are its sentences, its paragraphs, its chapters, its themes, and then its core ideas? Or if it's an image, what are its pixels, its edges, its objects, its scenes, or its concepts? So breaking down what is the essence of this representation. Then you analyze the missing pieces within that. So, for example, with the book Moby Dick, what would be the perfect conceptualization of Moby Dickness? And like, what does the book not essentially show within this, right? And then so you give that to the AI. And then within that, that's where you construct the Platonic form of the representation. So then you understand that. So then in this instance, it would be you're looking for the timeless, universal, and free from noise aspects. You're stripping away everything else that matters. So to simplify the narrative of Moby Dick, it's a very simple parable about obsession. Like bottom line, it's about obsession. And that is the universal metaphor of the book. And that metaphor of obsession is represented through the whale in this instance, and then through that creature, right? And then, but that's the essence of the entire metaphor. Obsession via the vehicle of the whale. And then from there, you want to just essentially like evaluate and measure your results, right? Just like you would anything else. And then so by doing this, you essentially can create the perfect conceptualization of whatever it is that you're looking at. And you do this mathematically. The models do this mathematically, right? Like, so while we're just talking about this concept, and the end result is shapes that you can look at and actually visualize and actually plot out on a graph-like structure. What is actually occurring is just pure linear, like a lot of linear algebra, basically, right? And then it's a lot of linear, like a ton of mathematical equations, where the model is essentially creating and then plugging in these variables. So, and then so it utilizes a lot of calculus-based variables then to plug in those equations and to essentially solve for the shape of that representation. Really cool, really straightforward to me. So it is essentially goes back and forth and adds to the overall argument. What exactly is going on with these models? You're seeing coalescing on one end more and more around this, right? That this is just more and more research stating the same things, that it's all based off of topology and geometry, and that the models are utilizing shapes, creating shapes, and that's the whole concept that they're utilizing and doing forth and going forth within this. And that's why self-supervised learning works and why we're able to be moving forward with these tracks. And then so just simply summarizing this for you, I'll leave a link to both the research paper and the collab notebook. So again, research paper is cross entropy is all you need to invert the data generating process. If you like this type of content, please like and subscribe. Thank you very much.